So, good morning, everyone. Week number week number 6. It's week number 6? I think it's week number 6. Yeah, it's week number 6. Good. So, again, we'll start with the exercise. Just quickly rearrange the windows a bit. Great. Good. So, our first task in exercise number 4 was to work with wildcards. So the task was give typing and evaluation rules for the wildcard abstraction and prove that they can be derived from the abbreviations stated on slide 11 from week 4. What did we have on slide 11 in week 4? That was this. So in some cases we do not need a bound variable in a lambda abstraction. That is when it's not used in the body, that is in constant combinators the case. In this case we would like to be able to use a wildcard, for example lambda underscore typed as s dot t to abbreviate lambda x typed as s dot t, where x is some variable not occurring in t. Good, so let's get on to that. Good, so how do we do that? So we need a typing and evaluation rule. So let's first get started with a typing rule. And the typing rule for this would mean that we type something that uses wildcard. That is usually an abstraction. So we need a lambda underscore. Let's type this as T1 and T2. And of course this goes from T1 to T2. Let's call this T wildcard. Okay. So, what do we need in the premise for that to be true? Well, we don't care about all of this before here, so we can leave that unbound. So this needs to be the same type as this one, but in general that's fine. But in the premise, we need to preserve the context, of course, and we need to talk something about the body, and the body of course needs to be of type T2, otherwise we wouldn't result in this T2 over here. Good. And so how do we do now evaluation? Well, we do have this lambda underscore typed as, let's name it T11, not just to be confused, because we now have application, and let's call the body T12. And then we have a value v2, and of course we don't care about the value. We evaluate straight to T12 because it's wildcard. We don't need that. And that would be our evaluation rule for wildcard. And then we're done. How can we prove that they are derived from the abbreviations stated on slide 11 on week 4? Like how this thing in the bottom came to place. Well, as you know that like wildcards work in a way as sequencing, you can do the same proof as sequencing, and then you're good. Basically, that's the idea here. I mean, that was just that was a rather easy task, I hope. So let's see if there are any questions for that. Possibly not. Okay, if not, then let's just move on. So Oops, just a bit less. There we go. So 4.2 was all about ascription. So type ascription, that was this feature that you can ascribe any type to any term, as long as you can type that term as that type. Why did we use ascription? Well, mostly for documentation, sometimes to make the life of the type checker a bit easier. That's usually the case. So what is the task here? Show how to formulate description as a derived form. Remember, the derived form was a mapping between an internal and an external language, so we don't need to reprove all of the things ourselves. Okay. So, and prove that the official typing and evaluation rules given on slide 13 in week 4 correspond to the definition of a derived form in a suitable sense. Okay, let's do this then. So, first things first, there is slide 13 mentioned. Let me just quickly pull up slide 13 here. There we are. So these are the typing rules, evaluation rules and syntactic forms for description. And as you can see, like they work as you think they would. So you can ascribe a type to a term when that term can be typed as that same type. And it of course preserves the type, otherwise we would have a problem. And the evaluation rules also work as you would expect. So description does not do anything. It's just one more evaluation step more that does not do anything. Okay, good. So the task, just to go back to our exercise view. So the task was to formulate ascription as a derived form. Okay, let's try to do more of the. Let's try an easy example. Yeah. How does the derived form work? Well, you have a term. It's called TST. That's a term that uses ascription. Let me just write that better. TST. Yeah. And then you make a define equals. Yeah? So you define something. You define a ascribed form. Now, how could you do the same thing? Well, we could. What is this in case? It's a term that is like that fixes a type. And how would you fix a type in the untyped lambda in the simply typed lambda calculus? Well, there's only one point where you actually have the type in the syntax, and that is for a parameter of a lambda abstraction. So what you do is you reformulate that as as an identity function. X goes to x, yeah, of type t, and then apply t to it. That means that the input parameter must be of type t. That is fine, and it returns the same term. And this is what you basically did here. So that would be in a very easy desugaring of that. Yeah. Now, what you need to do is to check on this side that you can derive the typing rules on this side with this equality in place, and vice versa. And that should be pretty straightforward. You can directly take the rules from abstraction and application on this side and come to the same thing as on the left side. So for typing, that should be really easy, and for evaluation also. So what you basically do is you write the typing rules and evaluation rules on this side and try to come up with the same thing as you would with these ascription rules that we had on the slide. So Oops, no, we're not over yet. So what you would have here is this thing. How would you type this? Well, if you put a type derivation of this, then you would come to something like this. So this is pretty easy. And if you evaluate that down, then you have two cases. Either t is already a value, then you would derive to v1, and if it's not, you progress it down. And the thing is, if you do that on this side, you would basically come to the same idea. And that's how this proof basically works. So here you do the typing rules, typing derivation using abstraction and application. And here you do the typing rules for ascription, and then you would get the same. And then you do the same thing basically for evaluation down here, and then you would come to the same conclusion. Good. Second part, not so easy. A little bit more complicated. So suppose that instead of the pair of evaluation rules e-ascribe and e-ascribe1, we had given one eager rule. So we would have now t1 as t evaluates to t1. We call that e-ascribe eager. So that would work. And that throws away ascription as soon as it's reached, as it's named here. Can ascription still be considered a derived form? Good. So for typing, that does not change much, but for evaluation it does. And if we do that, we would find out that we cannot use this anymore, because evaluation on this part works a little bit differently. So we need something that also eagerly evaluates on the other side. And the choice that you can do here, there are multiple solutions to this, but this is, I think, one of the elegant ones, is you do the following. You define a lambda function that takes a unit, and that it takes a function from unit to t and applies x to unit. And I would write here, but I don't have enough space. So let me go over in the next thing, and then apply that to a lambda function that takes a unit and returns t. You only need to preserve that y is fresh. Not that it's used anywhere. And then you basically have the same thing. What happens now is you mimic the basic behavior of that. You can basically use any other type as unit, just as a thing. It's intuitively correct. It does not give us the same derived form as for sequencing. This basically looks like sequencing up here. This doesn't. And the reason for that is that your desugared form basically takes 2 steps, and while this one is evaluated down in 1 step. So it's not entirely the same. However, if you only think of multi-step evaluation, then it would work. There is a little bit of a longer argument for this in the solution sheet, but in general, that's the part. for that. The idea is just that this needs to take 2 evaluation steps to actually evaluate down to the thing you want, while this takes just 1. Here. You could, of course, you can just make this thing a little bit more complicated so that also evaluates in 2, but what's the point? Good. No one has a question. And live attendance is surprisingly low today. Let's move on. Good. Let me start a new page here. Okay, so 4.3. Desugaring let as an immediate execution. So another way of defining let as a derived form might be to desugar it by executing it immediately. That is, let x equal t1 in t2 as an abbreviation for the substituted term x substituted by t1 and t2. And is this a good idea? Hope you all did that exercise because it's a really good exercise. So the thing is, this definition doesn't work very well. Yeah? It changes the order of evaluation. Yeah? So if you recall, let me see if I have the slides for that. If you recall the slide for the let bindings, there we have them. Good. So if you recall that, the interesting thing here is that the T1 first is evaluated down to a value. Yeah? This is the elet rule. So the T1 is first evaluated down to a value, and only if it can be, like, it is reduced down to a value, then it is substituted in T2. And this eager approach that we had over here, there we go, that doesn't do that. So it's not the same thing as before. In a purely functional sense, it wouldn't make any change to the result. But remember that we introduced side effects lately, and there it does, like, evaluation order does make a difference. Also for efficiency reasons, but that's a different thing. So, where was I? So we conduct that this is not a good idea because it changes the evaluation order. Another thing is, although you basically have the typing rule, the t-let rule, there we go, is actually preserved by this translation. In this typing rule, the evaluation order does not make a difference, as it should in a typing rule. But we just checked. The property of ill-typed terms is not preserved. So let us consider something like this. So let x equal unit applied to unit in unit. Now, and this is translated to the well-typed term unit, since x does not appear in the body of unit. And then this ill-typed term here, unit applied to unit, this just simply disappears. And this is also a problem, because then your type system would actually allow ill-typed subterms. And so the thing that we learned, that evaluation and typing are independent and should be independent, as least of now, is still true. But the thing is, if you have ill-typed subterms in a term, you may still type it, but you have ill-typed subterms. That's also not something you don't want. And this comes sometimes with evaluation order if you don't carefully manage your evaluation order. Good. Exercise number 4. Yep. If and case. So there is a similarity between the typing rules for case and the typing rules for if. If can be regarded as a simpler form of case. Now the idea was to formalize this integration to define true and false and if as derived forms using sums and unit. Good. How do we do that? So we generalize the if now to a sum function. And the first thing that we need to take care of is, of course, the type. So you have the Boolean type for the condition. And you need to define what you do there. And we define it as unit plus unit, because you need to distinguish if you have the true case or the false case. Remember, in sums you do this via the type and not through the evaluation. So how do you define that? So true would then be defined as inject left unit, because you don't need any more information, you only need unit. And then you define false as inject right of unit. And then you have the distinction between the true and the false case. And now you can use if T0, then T1, else T2. You can take an if term and define that in a case format, saying case T0 of inject left x1 should evaluate to T1. It's a true case. Inject left is true. Or inject right x2 T2. And of course x1 and x2 need to be fresh. And that's basically what you need to do. So let's walk you through this a little bit. So the idea here was that you can define such a derived form between the more special case of if to the more general form of case, which is part of a sum type. Good. So you have the Boolean as the unit type, unit plus unit. So you need to distinguish between left and right. True is the left part and false is the right part of the type. So this or this, basically. And then in the case, you distinguish between the left case and the right case. And just you take this T0, which is now of this unit plus unit type, not bool anymore. This T here it's bool. Here this is bool, and this is this unit to unit type. And the inject left case is the true case. So then you take this term, and then the inject right, you select this term. And then you basically have built an if as the sum type. Good. Any more questions on the exercise before we take a short break and move on to the lecture? It was a quick exercise session, by the way. It also was a small exercise. Good, doesn't seem to be the case. So let's take a short break and then afterwards talk about subtyping, new topic today. So see you in a bit.
Mais je te swing comme s'il était faux. Même toutes les rats sortaient sans trou. Venez tous, chaque soirée je dans la rougette des zombies dans son chapeau. Dab dab, vidi 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 ba. Les rois du jasmineux, ma béni de ma. Innocent sentimental, venez tous. Ces soirées je dans la roue, les rois du jasmineux. suelo vigila la tarántula. Ve con cuidado, desde el techo vigila la tarántula. La tarántula vigila. Desde el suelo, desde el techo. La tarántula vigila. Desde el mar y desde el cielo. La tarántula vigila. Desde dentro de tu mente, la tarántula te puede picar. La inyección. Si te pica la tarántula, no hay otra solución. Si te pica la tarántula, aprende la lección. La tarántula te puede picar.
So, welcome back. It was a very quick exercise session today. Nevertheless, we have some more time for the main topic of today, which is subtyping. So, subtyping is something that you are very well aware of if you have already programmed in a programming language like Scala or Java, which you all have. And so you know that you don't only just have types such as bool, but you may have subtypes. So bool does not have a subtype, but all your defined classes may have defined subtypes. No? Good. So let's look at what we have right now in our current type system for the simply typed lambda calculus. Yeah? So this is the application rule. So the application rule says, okay, you have a function that is the t1, and you have a parameter to this function which is t2, and you apply t2, the function t1 to the parameter t2. And of course, t1 needs to be of a function type going from something like t11 to t12, and you have this parameter which needs to match the input type of the function. This is all nice. But what if you have something like this? And did we already have records? Yes, we did. If you have a record like this, so you have a record stating, okay, you have a parameter to this function which says, okay, you need a record exactly of this in this form. So x is a natural number. And then you apply this to a record that has x, but also has y. Currently, this wouldn't work. Why this is the case? Because the type of the parameter does not match the type of the formal parameter. Does not match the type of the actual parameter. So this r is not directly what you have on the right type-wise. So this term would not type check, even though it will properly evaluate. So this is a little bit conservative. And this is the case because the types do not match. To pull up the chat window, by the way. Yeah, now I see you all. Great. And this means the types don't match, so you cannot apply this function to this record, even though it would like technically work. And this is like a bit disappointing. I would like to change this today. Yeah, and this is the reason again, because the type of the argument must match the left part of the function type. And if this is not matching, then of course this wouldn't work at this point. Well, the idea is now that we relax the typing rules by a thing called subtyping. We define types that also match the upper types, and for this we need a new relation, and this is this subtyping relation that we have here. So we say that S is a subtype of T, and T is a so-called supertype of T. And that means we can safely use any term of the type S in a context where a term of type T is expected. And this is the principle of safe substitution. This is quite central. This means that we can use any term of S for functions that expected T. That says we give a guarantee that anything that worked for types for terms of type T also works for terms of type S. And this is quite a strong guarantee, and this allows you this allows us to relax that type system a little bit, so we can make things like this record happen. We need to bridge that gap between like the typing relations that we now have and subtyping relations, because we also need to define what is a subtype of a type. But the first thing that we need to do is we need to kind of adapt the relation, this three-place relation that we had before of gamma T and big T here, to this new relation of S and T, this subtyping relation. And this is the so-called subsumption rule. And this is putting into a rule the intuition that we now that we just previously explained. So this basically tells us whenever you use you have a term of type T, you can use a term of type S. You can type the same thing as S, and also would be fine. This then helps you in a derivation tree whenever you have let's say a function parameter and that is typed as T, that you can also type as SS as long as S is a subtype of T. So this is kind of our adapter into the subtyping world now. So general properties of subtyping, something that your intuition tells you, but we now formalize this as well. So subtyping is reflexive and transitive. So whenever something is a subtype, it is also a subtype of itself. That we need to do in order to be a little bit more flexible when it comes to applying these rules. Sometimes you have it on the left and sometimes you have it on the right side, and if it's the same type, it doesn't matter anyway. So a Boolean can also be considered a subtype of a Boolean if you need to. However, it's the same, so it wouldn't make a difference. So you can safely do it as reflexive. And also it's transitive. That means if you have an intermediate type U in this case, and S is a subtype of U, and U is a subtype of T, then S is also a subtype of T. And that allows you to have kind of inheritance trees. What do I mean by this? Well, this is the case when you have a type that has a subtype that has a subtype. Then this lowest subtype, this one here, and this is in the middle, and this is the upper part. this here is also a subtype of this. Would make sense. This is something that when you have looked at inheritance trees in Java a lot, you find very natural to look at. So keep in mind, subtyping is reflexive and transitive. And I just found out that I forgot to start the recording again. So let's do it from here and cut the scene from YouTube when I get it. Oh wow, okay, it's going to be fun. In any case, you have the full stream on YouTube anyway, so don't worry. Good. Rules for record types with subtyping. And now we need to define something for record types. So records were our initial example that I showed you before. Just recall this one that I had here. This is a record, and this wouldn't work. So let's try to define that in a way that it works. Good. We need to actually introduce rules for particular extensions. We cannot just simply say works for everything, because we need to actually define what is a subtype of what. And in this case, we defined a rule for the width of a record. So we say that when we have a record, that's the thing on the right side, this li typed as big Ti, where I goes from 1 to n. We can also have a subtype of that, L of I, T of I, where I goes from n plus k. So a subtype of a record can be longer than a shorter type. However, the types of the part on the left side need to match the types on the right side, at least up to n. We don't have any information for those going up to k, n plus k, but at least from 1 to n, this needs to work. Almost. No. I have a bit of a cold, sorry. Yeah, this is subtyping that you just said. This is also subclassing, something that we will learn a little bit later, but in a way, so the term that you did is not actually subtyping, but it needs subtyping to work. So in this case, we have much simpler types right now. We have things like records. And there you need to have and you get in your mind that the longer record is a subtype of the shorter record type. Good. So in this case, this x equals 5 and y equals 42 record is typed of xnet, ynet. You can also search a super type that you can use your record into. You can also use this record instead of an empty record. Because then n is 0 and k would be 2. That would also work. If you've defined it now for the width of the record, so how long it goes, you can also go into the record and do a so-called depth subtyping. However, the types in this width subtyping still need to be the same exactly. However, we just learned that this might be a little bit conservative, so we introduced depth subtyping. So that means that we can have a record that has subtypes of the types defined in the other record type. So again, look at this rule. So the RCD depth rule basically tells you whenever you have a record that is li typed as ti, I goes from 1 to n, then you can also have as a subtype a record type that goes from 1 to n, but uses this si type, where for each I, si is a subtype of ti. Yeah? And remember that it's reflexive, so si can also be ti. You can also still use the same type. However, you can also use subtypes of the types you use in the supertype record type. Yeah? So that means that you can have things that vary in length, but also that vary in depth. So if you have a record type that has as one of its label types another record, that can also be a shorter record than defined in that term. For instance, if you have an X, a record consisting of X and Y, and X is another record type that consists of A nut, B nut, then you can use that term down here, this X equals this record of A equals 5, B equals 12, and Y equals 42. And you can type this as the exact type of this. However, you can also type this as X is a record of A nut and Y nut, of course. You can also leave out the Y whenever you feel like that. That's also happening. That depends on the context you're using it in. And the final rule allows us to reorder the fields of a record. Remember that the order was given by this sequence of LIs and TIs. However, you can find a permutation of that, and that's considered to be a subtype of this. So you can reorder stuff in a record now. You could basically, by the way, you couldn't do this before, and now you can. So that means you have this record of Y bool, Z string, and X nut. And of course, you can find a subtype where you sort these labels alphabetically, and you have X nut, Y bool, Z string. That also works. You have a question for slide 8. So what's your question for slide 8? Just move back. Sure. You mean these two? Yeah. Last line on slide 8. Yes, you can. So you can now write this as X X A nut. You could do that. You can just leave out the Y. Yes, because that's again the width subtyping. So when you go into the this X this type for X, and X is a record of A and B. And then you can use the width typing again and define a subtyping relationship between those two types, and say X is now a record of Y. Oh, you just didn't define this. This is fine. You can have subtypes that don't define all the things in your record. However, if you use a term in that context, Y cannot be accessed anyway. So we don't need a type of Y. This will get Just bear with me for a moment and you will understand this a little bit better. Yeah. If you leave out y in this typing, there's no way you can use it in a function anymore. However, still it's in the term. No? You will see this in a minute. So permutations, pretty easy. And now you can use these three rules, this sRCD perm and sRCD width and strans rule. No? One more thing, yes. By the way, just type in the question. No need to just raise your hand. I think I missed one question from Aman. No. I actually answered that before. Good. So moving on. You can now like use the three in combination, yeah, to drop fields not at the end, but anywhere in the record. So you can just drop the X, you can drop the Y, or whatever you feel like. Yeah. You can use all of these in combination. Though it's pretty flexible. It's pretty neat. Now we need to talk a little bit about function subtyping. So the one thing that bothered us in the beginning was not only that records cannot be typed as other records, but its application to a function. And the idea now is that we have a subtyping function for function application, which works a bit like this. Yeah? And this is a little bit too hard to wrap your head around. So let's say you have a function type t1 to t2, and you want to subtype this to a new subtype, and this is s1 goes to s2. So now the input parameter, the input parameter of the function type on the right side must now be a subtype of a more general type S1, a super type to T1, and T2, the result type, is a subtype of that thing. So as an argument, the function may accept any subtypes of S1, but its result will be at least T2 or a subtype of it. So it's a little bit crossed. But once you use that, this will become very, very natural. Just think of these things are a little bit twisted around here. So subtyping, and the subtyping is in the same direction here for the output type, which is called covariant. And this is sometimes you find in language definitions, especially for newer languages, when they talk about covariant and contravariant parameter definitions. In Scala, you can actually define that. You can define if your function is covariant, contravariant, also called invariant. That means that it only accepts the type you defined. And this is rather interesting to me because as a programmer, it leaves you a lot of more design choices than before. However, here for the lambda calculus, we fix it now and say that for parameter times we need contravariance, and for the output type we need covariance. And basically it's the same as I read it. So as an argument, the function may accept any subtypes of S1, but its result will be at least T2 or a subtype of it. What we also need is, now we've given you like basically a tree, we need an upper type bound. And this is only a theoretical concept. And it's much more usable if we give it an upper type bound, because then we can always revert to that whenever we feel comfortable with that. We cannot do anything with that, but in general we can have that in proofs and whatever. And we need this to be defined like this. So for all the types S in the world, there is a supertype called top, which is a supertype of that. In the Scala type systems, you actually have such a type that's called any or none. I always forget how it works. I think it's none. And a more general type called any. Oops. Just at this point, think of it as just your upper bound to anything. Oh yeah, thank you, it's any. I always keep confusing it which way it's around. Good. Let's look at the lambda calculus with subtyping. So terms will stay unchanged, values will stay unchanged. However, we will introduce this top type on the type level, and our type environment will unchanged. So little to nothing in syntax. For typing, also not much. We need this new S sub rule, but the other rules, tvar, tapps, and tapp, we don't touch. No? And then we have introduced subtyping, which is neat. However, we then need subtyping rules. And these are the subtyping rules that we talked about. So reflexivity and transitivity. So subtyping is reflexive and transitive. You can always exchange it with the same type on left and right. And you can find an intermediate type. If you can, then you can have transitivity. You have this top type that is the super type of everything. And this is the S error rule that I explained to you a few slides before. And then, of course, you need subtyping rules for all the things you extended the language with. In this case, it's records. So these are the three rules that we introduced before. So it's the width rule that allows you to have records of varying length as subtypes. And then you have this depth rule, which allows like subtyping in the actual record types. And then the permutation will allows you to just basically reorder stuff as you see fit. No? So these are the new rules that we have. And let's do some sample derivations. Like the colors are just here for easier navigation. They're not part of the syntax. They're just so you know how we progress this along. So we want to show that the type on the left side is a subtype on the type of the right side. And as you can see, they're not equal. So X has a different type and Y has a different type, but there's an X and a Y. So let's see. So the first rule that we apply is this sRCD depth rule. The sRCD depth rule gives us that we can show if these rules are in a depth relationship. So this green part, A nut, B nut, needs to be a subtype of the X on the right side, which is A nut. And M nut, which is the type of Y, needs to be a subtype of the empty record. And now we need to come up with derivations for these parts, for these premises. So let's look if we can do that. So the sRCD width rule gives us that we can do this. And on the right side, the sRCD width rule also says we can do this. So we can just we just have shown that this is a subtype of this. Why is this the case? The sRCD width rule says we can also have as a subtype a record that has more fields than the thing on the right side, but at least the ones on the right side. So for the right premise here, this M nut, so this orange and blue thing here, this is very natural because like on an empty record, you don't need to repeat anything. And you can just add stuff, in this case M nut, and this is fine. Same goes for the left part of that tree, because you added a B, and you have this A in the left side and the green part as well. So this pretty much works. So you've shown that this is true. Let's do this a little bit more tricky example here. So we need to show that the green part here is a subtype of the blue part. And if this is the case, how do we begin? Well, we take the S-trans rule, and find that there is an intermediate type, which just leaves out the Y of the green part. So this orange part leaves out the Y of the green part, as you can see. But other than that, it's pretty much the same thing. And we need to show that this is actually part, these two premises actually also hold. So let's start on the right side again. For this, we need to have the RCD depth rule, because in the orange part, X is a type of A nut and B nut, and we need to show that these two are basically in a subtyping relationship. So this light orange and light blue one now, and the SRCD width rule gives us that without any premise. This is fine because we just left out the B. This is fine, so this is good. On the left side, the SRCD width rule strikes again because Y is also just left out, and then we're good. And then we again have empty premises, so we have actually shown that this is true. Let's do something with functions and tsub. On the bottom part, I left out a few things, and I made this for easier navigation a little bit more tractable. So F is lambda R of type X nut, as like a record, and it's a projection to the X part of R. So it selects whatever is an X. So that's F. This XY thing is just a syntactic thing. It's actually one thing. It's not an X applied to Y. It's actually XY. And this is a record that has X is 0 and Y is 1. And of course, the type of X in that function is record of nut, because it's defined here. And the other thing here, this XY, has, of course, a record called X nut Y nut. And now the idea is that we can type this under no assumptions as a natural number, this F applied to XY. So let's see if this is true. Okay, let's look at the application rule first. So let's apply that first. And the application rules tells us that XY must be of type X, Tx, and F must be a function going from Tx to natural number. Okay, we can see that this is this usually holds, but let's look into that. So on the left side, we leave that out. This is just like finding that projection works. We already did that. That's basically just the record rules. This works fine. On the right side, it becomes more interesting because we need to use the tsub rule. And for the tsub rule, we can say that, okay, under no assumptions, xy can be typed as txy, and txy is a subtype of tx. We just state that here and say, let's look if this is true. On the left side, so let's say xy is txy. We look at, okay, well, txy says like x is not and y is not, and this t record rule tells us, okay, 0 must be a natural number and 1 must be a natural number. This is obviously the case, so we're good. On the right side, we can use the SRCD width rule because we just left out the y. So pretty easy thing. And we don't have any premises more, like we don't have any proof obligations, no empty premises to only empty premises. So we can say this is also a working derivation. Huh? Good. Now comes the part you all feared, of course, and this is proving that we still have progress and preservation. For this to actually work, we need some helper constructs, and to make the proof for preservation and progress. Well, because we just added subtyping, which is like a major thing, and we need to check if like our type safety is still guaranteed by our type system. So, of course, as with all the others, you are pretty much familiar to the concept. We need to inverse the subtype relation first in order to use it as this. And this gives you basically the two things here. So if S is a subtype of this function type T1 to T2, then S has the form S1 to S2, where T1 is a subtype of S1 and S2 is a subtype of T2. No? And the second thing that you hold here is that if S is a subtype of this record, and S has the form KJ SJ1 to M, and at least have the labels L1 1 to M, then L1, that means that it's like a subset. Subset meaning you don't have particular order, which is nice because of the permutation rule. And for each of the types Sj, you have a type Ty, which is a supertype in that other record for each common label. So this is just inversion of the typing rules that we did. Then our helping constructs. So the first thing that we need to establish is if you have a well-typed thing, a well-typed function, such as this, where lambda x is of type big S1, with the body of small s2, and this is typed as T1 to T2, then T1 is a subtype of S1, and also under the assumptions of gamma and x is of type S1, S2 can be typed as T2. This follows very naturally from all the rules you had before. But it's one sentence that you need more. And you can prove this by simple, straightforward induction on the typing derivations, using this lemma that you had just before and the T sub case. That's really pretty straightforward. You can do this on paper if you like, and find you can really easily do this. It's pretty mechanic. Interesting. The chat just failed. Database error in Panda. I love Wednesday mornings. Oh yeah, okay. Panda seems to be down. No fear. We just continue with the stream. Will be a little bit less interactive now. Let's see when it comes back on again. Okay. Yeah, now it becomes less interactive. Sad. Good, so then we need the substitution lemma. And we actually do not need to change the substitution lemma that we already have. But we need to simply slightly change the proof. So our substitution lemma, remember, like we just modeled a little bit with the function types, introducing subtyping there. Oh, Panda, back up again. Great. Open the chat again. And hope you all join again. Good. Yeah, so welcome back. I love Wednesday mornings. It's so good. Substitution. As I just said, we don't need to change the substitution lemma, but we need to change the proof, as we did a little bit muddle with the things going into function application. And remember, substitution worked like this. So if you have under the assumptions of gamma and that x can be typed as big S and t can be typed as big T, and S is well typed as small s is well typed as big S, then you can also, under the assumptions of gamma, exchange x by s in T and then type this as T. Substitution lemma as we had it before. So the proof basically works the same. You do an induction on typing derivations as usual. But we need new cases now. We have new typing rules, and we need to use these new cases, T sub, and for the record typing rules, T RCD and T projection, and we now make straightforward use of the induction hypothesis. The interesting thing is it's just like the proof for the substitution lemma itself that we already did. It's just mechanically applying this the same principles now to the new rules that we introduced. And that's why I leave it out, because it's only mechanic. You can do this, but you will get bored pretty soon. Preservation. Also, preservation theorem is the same. Proof is more complex. Same thing as with substitution. For preservation, this does not need to change. This is still a good property. Most of the cases that you now have, because you have new rules that you basically need to do, is absolutely similar to the proof of preservation for the simpler type lambda curves that we did before. We just need new cases for the record typing rules and for subsumption that you had before, but that is just, again, mechanically applying the same principles as before. And that's why we introduced these helper constructs as well. Let's have a little bit of a look. Okay, panda down again. Great. Well, let's just continue. Good. So for the TVAR case, we don't have evaluation rules for variables, so we don't need to preserve things. And TApps, we also need to talk about this because T is already a value. T application. That means from the evaluation rules of the lambda calculus, we see that there are 3 rules by which T can progress to T prime, which is EAP1, EAP2, and EAP-apps. And we just proceed by these cases. So the subcase EAP1 progresses the first part, and the rules follows from the induction hypothesis and TApp. So this is just recursing basically in your proof. EAP2 the same. And the EAP-apps rule is the actually interesting thing. And there now we need our new lemma. This is now the interesting part where the proof gets a little bit more interesting, where we actually need the things that we defined before. Okay. And we have a panda chat again. Sorry for that. I don't know what they do. Is this like a usual window for their... Let's just check. No. Everything green. Oh, and it's down again. Well, let's not bother for today. Please write your questions down and put them into the Panda forum once it's back up again, and let's disregard the chat for this week. Ugh. Good. So, where were we? The EAP-apps case. So this is the interesting part. This is where we need to introduce subtyping. And as you can see, it's a little bit different here because we have now the subtyping, this this S11 type. You know? And you can use now that this S11 type is a supertype of T11. You know? And add this to the environment here, so gamma and XS1. Under these assumptions, S12 is T12 is typed as big T12. No? Remember the lemma that we introduced before? This is the first part that we apply right here. No? And then you can use the T sub rule, saying, because it's a subterm, T2 is now of type S11 by the T sub rule. And from this and the substitution lemma that we introduced before, we obtain that T prime is again T12. And this means we preserve the type. Pretty neat. For records, there's not much that we need to do, but the only evaluation rule whose left-hand side is a record is ERCD. This makes the proof also very easy. So whenever you design evaluation rules, also make sure for the proof that you don't have so many cases like this. And from the premise of the ERCD rule, we see that Tj progresses to Tj prime for some field of Tj. Because ERCD, if you remember, it progressed all the parts of the record down to the individual parts. And the result now follows from the induction hypothesis applied to the corresponding assumption that Tj is of type big Tj and this TRCD rule. So basically you just push it down to the individual field and then you preserve. Projection, this becomes a little bit more interesting. And from there, from the evaluation rules for the record extensions, you see that you have two rules by which you can progress T to T prime. And this is E-projection record. And E-projection is just is the actual projection rule. And no, that's the actual progression rule, that you actually like progress things down to values. And this follows by the induction hypothesis, because you don't evaluate the projection itself yet. You just progress the record down to a value. And this is the case we have just shown with the TRCD rule. And this is follows then from the induction hypothesis and the T projection rule. Good. E-project record now is the actual projection. And there you now need to have this lemma. And then we need the second part of the lemma be introduced. And then you have that Lj is Li is a subset of Ka. And Va is typed as big Ti under the assumption of gamma for each Ka which is Li. And in particular, that's also true for VB typed as Tj, and this is as desired. And then you have proven the subcase for E-project record. So pretty neat, pretty straightforward also when you have established these lemma beforehand. Good. And T sub is really easy because by the induction hypothesis, there is a T prime as S, and by T sub, S is a subtype of T, and so you can also type T as T, and this works pretty neatly. No? Good. Canonical forms lemma. We also need to update this a little bit. And this is because we are using this in the closed values. We changed the closed values a little bit. So if V is a closed value of this type of this function type, then V has this form axis S1, axis of type S1, the parameter, and the body is T2. And if V is a closed term of that record type, then V has the form of Kj equals Vj, where Li is a subset equals to Ka 1 to m. No? This just means that we pushed subtyping now also into the canonical forms lemma. And why do we need the canonical forms lemma? Because we need to prove progress as well. Yeah. And now we have pushed most of the burden into this canonical forms lemma, and only a few changes need to be made here. So if T is a closed well-typed term, this is why we need the canonical forms lemma, because we need to define what closed means. Then either T is a value, or else there is some T prime where T progresses to T prime. Classical progress rule. And you can prove this now by doing a straightforward deduction on the typing derivations. In general, like the variable case cannot occur because T is closed. We just established that. The case for lambda abstraction is immediate, since abstraction our value is also. And like, let's look at the remaining cases here. And for this is application, and the application case is one of the most interesting things here. And by the induction hypothesis, you either have a value in T1, so this is the function, so this is either value, or you can make a step of evaluation. Likewise for T2 as well. And if T1 can make a step, then the EAP rule applies to it. And if T1 is a value and T2 can take a step, then the EAP2 rule applies. And finally, both are values. Then you use the canonical forms lemma that tells you that T1 has this form, and so the EAP-APS rule apply. So you have the three cases that either the function itself can be progressed, the value can be progressed, and if both cannot be progressed anymore, then you have this form. Then you have this form that T1 is of this lambda x big as 11 dot T12. So the EAP-APS rule applies to it. Good. The case for T record. So you have a term that is a record. So something that is a label and a term for going from 1 to n. And then for each I, you can establish that all parts of the record are already well typed, Ti as big Ti, and T is then like a record of these types. So this is straightforward. Record definition, nothing new. Good. Before we continue, let's give Panda one more chance. It's much more fun if it's interactive, isn't it? Aha. Okay. Seems to be back up again. Chat seems to be back up. Let's see. If it fails a third time, I just disregard it for today. Good. So we have established the basics for the T record case. Now the proof. So by the induction hypothesis, Ti is already either a value, or you can make a step of evaluation. If all of them are values, then T can take a step. Then T is a value. The whole term is a value. And on the other hand, if at least one can make a step, then the rule E record applies to it. So progress is given somehow. Other case, it's the value. Good. Projection rule. The projection rule. So by the induction hypothesis, here again, T1 is either value or can make an evaluation step. Seems to be straightforward. So if this T1 that you have here can make a step, and the rule by doing that is the projection rule, so can T. And if T1 is a value, then by the canonical forms lemma that you had before, 1536, then T1 has the form of Ka is Vja going from 1 to m, with this subset relation in place. And then Vj is well typed as Ti for each Li which is equal to Kj. So in particular, this label Lj is among the labels of Ka from T1, and Lj is the label you need to project right now. That's the thing that you have now in the projection. That is among these labels of T1, from which the rule eProject record tells us that T itself can take an evaluation step. So you've shown the projection case as well. Good. T sub again follows from the induction hypothesis out of the sky. You don't need anything fancy for that. That's pretty neat. Good. Yeah, that concludes the proof, by the way. And then you've shown that we now have safely introduced subtyping into the simply typed lambda calculus, which is quite neat. Good. So we already learned that type top. Let's now introduce also a lower type called bottom. And bottom is the subtype of every type, and it is empty. That means you don't have any closed values of this type. So no value can actually take that type bottom. So it's a rather academic thing. This seems to be absolutely useless at first glance. The thing is, it's quite convenient to say that some operations are not intended to return. This is pretty useful for throwing an exception or invoking a continuation. This is the two cases where bottom is really, really neat and really, really elegant. In other cases, again, rather useless. So its only value basically is to signal the program that there is no result to be expected. And on the second hand, it signals the type checker that such an expression can safely be used in any context expecting any type of value. Unfortunately, the thing with bottom is that complicates our implementation of the type checker significantly. If you are adventurous, you can use your own type checker implementation to implement the bottom type and implement the rules for the bottom type. It is rather complicated and not very helpful in summary. So let's disregard the idea for now. We come back later to this bottom type when we have a few more tools at our hand to actually make use of that much more. So for now we stay with the top type, but I just wanted to introduce you the bottom type because at some point in proofs it may be necessary. But alas, when it comes to implementation, word of warning, leave it out. Because it complicates things much better. Good. We have done pretty quickly today. I will just take a bit of the second part of the subtyping and pull it for today also. So all that you've seen until this point is based on chapters 14 and 15. So that's the basics of subtyping. Let's take a 5-minute break and then come back and explore subtyping a little bit more, okay?
Porca troika!
Solo sabes que no quieres tener que pedir perdón, pero no sabes lo que quieres. Bueno, pues ya somos dos. No sabes si lo que tienes es tan solo la mitad de la mitad de la mitad de lo que puedes tener, de lo que puedes perder. Mira por la ventana a ver si ha salido el sol. Si llueve ven a la cama, vuelve a saltar en calor. Van pasando las semanas por el retrovisor del autobús que pasa delante de tu lugar, sin que te puedas bajar, y echamos a correr hacia el resto de la vida. Resulta que al final era el punto de partida. Echamos a correr sin saber que nada se puede retener, que será, será, seguirá. Solo sabes que no quieres tener que pedir perdón, pero no sabes lo que quieres. Bueno, pues ya somos dos. No sabes si lo que quieres es tan solo la mitad de la mitad de la mitad de lo que puedes tener, de lo que puedes perder. Echamos a correr hacia el resto de la vida. Resulta que al final era el punto de partida. Echamos a correr sin saber que nada se puede retener, que será, será, seguirá. Que será, será, seguirá. Que será, será,
Good. So welcome back. Just quickly today, I wanted to add a few more things. That's actually on the slide set for the next week, but let's do this today as well because we're still like in the topic, and then we can start with a more advanced topic in the next week. Not be too ripped apart. So we talked about records in subtyping, and now let's revisit some of the extensions that we already had before and do them as well. Good. So as I said before, like, let's review all the extensions that we had before, and then try to come up with their compatibility to subtyping. These are all extensions to the lambda calculus that we already discussed, that you already know or should know, and we just adapt them to be compatible with subtyping. So ascription and casting. So up until now, like ascription, as we had it like in the exercise before, it has just pure documentary value. So nothing really good, nothing really helpful. But now we have subtypes, and it's actually our casting operation. So if you are familiar with Java, and most of you are, then you know typecasts. And ascription is basically what we now use as typecasts. Yeah? And so an upcast from a term would look like this. So T is typed as S, as T, and this will type check if S is a subtype of T. Yeah? So you can go upwards in the relationship and go for and ascribe the supertype as you wish. Yeah? So let's look at upcasts. Let's show this. So T as T, typed as T. This is true by the T ascribe rule, of course, and then we introduce the T sub rule, which says okay, T can also be typed as S when S is a subtype of T. Yeah? And the premises for that are to be checked. Yeah? But in general, let's say they work out, and then you have made an upcast. Yeah? So this is how ascription basically works with subtyping. Pretty neat. Downcasts are a little bit more complicated. You also know this from Java. So when you do downcast, you may end up in a case where you cannot do the downcast because your assumption that the object that comes into your function is of this particular type that you cast it down to is actually not valued. And this is the rule for downcasts. So T as T is of type T when you can type T1 as S. Yeah? Relationship. However, we have a rule now that allows us to do that. This allows a variable of any type to be cast to T. So this is basically what a downcast is. But do you want that? I don't know. So leaving it like this will actually break your progress property and therefore also type safety. So this is insufficient. So the idea here is to program this in a way, or to design this in a way, in the principle trust but verify. Thus, the type checker trusts the programmer's ascriptions, but inserts new checks for the evaluation for the runtime engine to allow safe evaluation if types will not check out as valid. And this is exactly what your Java virtual machine does. It trusts that your downcasts can be made. However, in order to have a valid program state, they throw an exception if that's not the case, because they check at runtime if this is the case, and if it's not, they throw an exception. We want to mimic the same behavior now in the lambda calculus. And now this introduces something new, runtime type checking. Remember that during type checking, you should not use evaluation. Yeah? However, the opposite thing does not occur. So during runtime, you can use type checking to do runtime type checks. That's the opposite direction. This may work. So let's look at this. So you have an EScribe, and the EScribe says like, okay, if you have a value v1 as t, then you can progress that down to this value. This is fine. Yeah? And this simply throws away the type information. This is the present rule that we have. Let's modify this a little bit and call this eDowncast. And in the premise of this evaluation rule, force a type check and say like, if you can type check v1 as t, then evaluate it down. So now you have introduced a runtime type check into your evaluation system, into your formal operational semantics, not the other way around. Yeah? And this is how you do runtime type checks. Basically, you force in the premise that something is well typed, and then the evaluation needs to call the type checker to actually see if this is the case or not. Yeah? And this can be made at runtime because at runtime you know what v1 and t are, and then you can do a type check, and this will work. Yeah, this is the runtime type check. Of course, this also adds the complexity of your type check to your execution engine. So you don't want to do this very, very often. Yeah, this is why in all the Java books you find don't do so many instance of checks. And this is because the type checker then runs, and the type checker can run for some time. And if you do this like in iterations, in a loop, it can really be a burden on your performance. And we will still lose progress when someone attempts an invalid downcast, because then your programs will get stuck. Yeah, but we are now able to locate that a little bit better, and we now need some form of dynamic type test to complete this. So now we change this a little bit and do a new typing rule called t-type test. And t-type test has the form of a special if in this case. Yeah, it's basically a reuse in syntax. You can form this in a different way. In this case, it's been designed like this. So the way that it works is if t1 in t, then x progresses to then x progresses to then x progresses to t2, else t3. No, is of type u. No? Don't think that in this typing rule you do evaluation unless you have kind of an evaluation construct that you now type check. It's a little bit difficult to wrap your head around, but this is actually how this works. So you force that in the premises, then you force that t1 must be of type s, and under the assumptions of gamma and that x is t, you force that t2 is u and that t3 is u. Yeah. So both terms that come out are of type u, whatever that may mean. Just force that's the same type. And then you have two new evaluation rules that use this new type check construct. Yeah? And now there is evaluation happening. Yeah? And see that this small error is not the evaluation error. The evaluation error is a longer one. Yeah? Sorry for the syntax, I just took this straight from the book. We could do this a little bit differently nowadays. No? So this says like, okay, you have two different cases. Either either v1 is well typed as t, or it isn't. Yeah? And if it is, then you exchange x by v1 in t2. This is why there's this little error. Otherwise, you just use t3. So now you have a backup plan. Now you have a backup plan when your runtime type check fails during downcasts. Now we can use this in the downcasts. Yeah. And as I already hinted to, like, downcasts have a downside. So you will add type checking to the runtime engine, and this complicates and slows down evaluation significantly. Before you needed to just check one simple premise. Now you need to do a whole type check for a term, which also may involve type checking subterms and subterms and subterms. This can be arbitrarily complex, so you don't have this in your hand anymore. Yeah. Sometimes type information is erased, so type information needs to be reconstructed. This is sometimes the case in Java as well, when it comes to collections, generic collections and so on. This has been tackled a little bit, but in general, sometimes this type information needs to be reconstructed, which is a little bit cumbersome in some cases. Yeah? And this is also why some languages and compilers preserve some type information in the compiled code. When you look into JVM bytecode, so the bytecode that actually is a compiled Java program, there you can see a lot of type information still in there. And this is to actually help runtime type checks, to be reconstructing type information from scratch. Good. One other interesting type extension that we looked at are variants. And subtyping for variants basically looks very similar to those for records. However, more or less in the opposite direction, because variants work on the type level, records work on the term level. That means that variants need to be a little bit different. Let's have a look. So quick recall. Variants. Variants are of these types. So this is a variant type. L1 is of type T and L2 is of type T2. And then you have one instance of that. So that means L1 equals T as this variant type. So it's basically a sum type with more options, as you can see. We had some types in the exercise this morning. Yeah. So this is the variant type. This is an expression using the type. Yeah. Remember that thing that we had, like get name of this address type. This is just to quickly recall how that worked. Good. So the intuition for subtyping now is a little bit different than for records. Yeah. So this thing type checks. So L1 equals T as L1 T1 L2 T2. This type checks. Should this type check? Yes, of course, this also type checks. And this is fine. Yeah. So is then L1 T1 a subtype of L1 T1 L2 T2? Adding more labels decreases the information about the elements. So remember, while on records on the left side of that relation, we had the ability to add new records things. Here now we have that on the right side. So the more labels you increase to a variant type, it decreases the information about the elements. And And this is the more precise type, actually. So this should be the subtype in this case. Huh? How do we do this? Syntax does not change very much in this case. It's the same as you know it. However, we do not need any description anymore. This is good. This is really nice. Remember, then we had this as and then the whole type of the variant. We don't need this anymore because now we can use the most precise variant type and just construct supertypes as we go along that are less precise. The T variant and the T case rules are also not changed unless that you don't have a description anymore, which simplifies this thing a little bit. But subtyping rules, and subtyping, these are the subtyping rules, the width, depth, and perm rule for variants. And as you can see, they look basically the same as for records, but the table's a little bit turned. So here on the right side of the relation, you can have more, while on the left side you have less. However, in the depth relation, you can basically do the same thing as with records. So you can have a more precise type in the subtype, of course, which is okay, which is nice. And then you can reorder, which is also okay for variants. This is the depth and the perm are basically the same thing as for records. Why can we leave out the description from the original rules? So this is an interesting thing. Let's say we have a well-typed variant expression like this, and it is typed as this L1 T1 L2 T2 variant type. Then we can use the width rule and come up to this more precise type. Okay, this also type checks in. For this type. Pretty neat. And then we can use the T variant rule to come up that T1 is of type small T1 is of type big T1, and then we're basically good. Oops. And this is we can do anytime. Oh, come on. The last thing is an auto animation. There we go. What I want to say, yeah. And this means that we can always fall back to the most precise type and construct in the other direction more imprecise types that we can use as supertypes. And that means we do not need the exact type anymore, because now we have the T sub rule and the S variant width rule to help us in cases where we would have needed description beforehand. And this is why we don't need it anymore. Pretty neat. Lists. Lists are an interesting thing because covariance and contravariance come into play again. And the list constructor as we have it here is covariant. That just like records and variants, a list of a subtype is also a subtype. A list of a subtype of T1 is also a subtype of list of T1. So if we have lists whose elements have type S1, and S1 is the subtype of T1, then we can safely regard our list as having elements of T1. This is very, very neat. And in Java, you don't have this. In Java, lists are invariant. So you need to really fill them in the, you need to have a defined list of that type, of that parameter where you want to bind your list to. Otherwise, you wouldn't do. Java programmers can tell you all things about conversions of list types and so on. In Scala, luckily, you can define that. So when you define your list type, you can actually say that it should behave covariant, contravariant, or invariant, while in Java, all lists are invariant. reference must be invariant. Yeah. So the type constructor for reference is invariant. This means that the type of the reference must always be this exact type. Do I have slides for this, by the way? Yes, I do. Good. So that means that like the type of a reference must always be the exact type. And why is this so? Yeah. By the way, this is a way to force equivalence if you just do subtyping relations in both directions. Yeah. So one must be the subtype of the other, and the other must be the subtype of a thing. Then it means basically they're the same. So this is a type equivalence in a way. This way we are open for equivalent types. So reordering of records is an equivalent type. So you can do reorderings, and the thing holds in the same, but are safe for everything else. So in references, you can do records with like switched out permutated things because the permutation goes in both directions. However, you cannot use the width rule because this does not go in both directions. So pretty neat. Also holds for all the others. And the thing is, why is this so restrictive for references? Because reference values of type reference can be used in two different ways, and this is dereferencing and assigning. And for dereferencing, here the returned value must be at least of type T2, of type T. So if S is a subtype of T, then we are good. This is nice. So, but for the assignment operator, if we assign a value of T to a references of type ref S, then someone might use this value as a value of type S. Therefore, T must be a subtype of S must hold. This will become immediately clear once you use references in that way as parameters to functions that do dereferencing and assigning. We will do this in the exercise. So bear with me for a moment, or try this out yourself when implementing that. And then you see that in order to safely use that, you must do this in both directions. Otherwise, it wouldn't work. Finally, arrays. Same argument for reference also applies to arrays. Thus, their subtyping rule is also invariant. You can use arrays in the same way. So the way we did arrays, implemented arrays, was with references. So the same rules actually apply to arrays as well. Interestingly, in Java, arrays are covariant. Arrays allow covariance. So that is an array of S1 is a subtype of an array of T1 if S1 is a subtype of T1. You can try this out. This was meant as a workaround because people were complaining about things, and they introduced that as a workaround. And this is actually now considered to be a serious flaw in the language design of Java. Because in some cases you actually are not safe in that way. What people do is they do runtime checks on every assignment to any array, which, as you've just learned, can be pretty costly. They did some tricks to make that more efficient, of course, but it's not very elegant, and they had to do these tricks to actually be at least somehow performant in that way. Right now they cannot change it anymore because people rely on that behavior, and this is all pretty annoying. So when designing your own language, possibly have a great look at covariance and contravariance, especially when it comes to subtyping, because it can produce all sorts of crazy stuff. Good. Before we go into implement subtyping, I want to close for today. This is basically, I think, the same chapter as before, 14 and 15. It's actually 15 and 16, but I think it's just 15. 16 we will have next week. So this was subtyping. at least the first part of it. Next week we will talk more about implementation, how to actually make subtyping work for your type checker. And this will also be relevant for the lab at some point. So be sure to pay close attention to that. Yeah, with that, I think 20 minutes a little bit before. We're closing a little bit early because the exercise session was pretty straightforward today. Sorry again for the panda issues today. Hope this was the last for today. And again, I'll upload these videos to the university video platform, and see you all on next Wednesday. Thank you very much.